camera cut out, but as I was saying, in order to find the resistance, we would need both the voltage and the current for this resistor right here. So that means we're going to need at least two pieces of information. For part A, it says that would measure the voltage from point S to T and from U to V. That's actually measuring the exact same voltage because this is the voltage of the battery and this is the exact same voltage of the battery. I didn't get two pieces of information there. I got the same information twice, so that's why I crossed off A. That was kind of redundant. B, you can see it's the right answer, but here I would get the total voltage, and then if I knew this voltage right here, well then I would have my V that I need. And then because I know the total voltage, I could just subtract this from the total to get this. So let's say they gave me a total voltage of 8, and I knew this one was, 3. Then you could say, oh, well then this is just 5 volts. 5 divided by 3, that would give me my current here, which is the current here. And if you know the voltage and the current, then you can find the resistance. So that's why B works. C, very similar. UV is, again, the total voltage. So if I know that, then I'm cool. And then if I get from W to X, well, I'll divide this by the resistance. That gives me the current right here. And then if I know the total, I can just subtract to get my missing voltage. And then I would know voltage and current. S to T and W to X, or W to Y, sorry, D. This is, again, redundant information, right? Once you have ST, you don't need this because you already know it. So that's why D is wrong. And these two only give you one piece of information, which is not enough. Number 7, so it says the sum of these two make 12, so I redrew it with 12 right here. And then I still have the 3 ohm, so I used the fact that I had the resistance and the current, and I multiplied it and got my voltage right here. These are in parallel, so that means the battery also has 6 volts, and this guy would have 6 volts. Not each of the two resistors, right, the combined 12 would have the 6 volts. I want the current through the battery, which is I total, which is V total over R total, so I'm going to take these, these. They're in parallel, so 1 over 3 plus 1 over 12, 1 over that gives me 4, I think. So then I have total voltage of 6 divided by a total resistance of 4, and that gives me a current of 2.5. Oh, my total resistance is not 4. Doing a calculator, so we should be getting, that's not right, 2.4? Yeah, 2.4. 2.4, and then 6 divided by 2.4 gives me a total current of 2.5 amps. Alright, the next one, so here we've got battery, I've got some internal resistance that is part of the battery, and we've got 2 resistors. R1 is the largest resistance, R3 is the smallest. None of them are the same resistance, which of the following is true. So here we're looking at the relationship between currents. So I see some are like equations, so I'm going to say, well, these two, right, I3, that's like my total current right here. And then when it hits here, it splits into 2. So I know that my total current is just these 2 branches together. So I1 plus I2. I1 plus I2 equals I3. Ooh, A is correct. I2 plus I3 gives me I1. No. The total plus a part does not give me the other part. That doesn't make sense. The next look like rankings. So let's say I3 is my total current. So of course I3 is bigger. Now between these two, I know these two have the same voltage, but their resistances are different, which means their current should be different. So current is V over R. If these are the same, then whichever one has a smaller resistance would have the bigger current. So R3 is smaller, but I'm not talking about that. I'm talking about these two. And R1 is larger, so R2 is the smaller one. So I2 is next, and then I1 would have the least current because this current that splits up less goes here because it has more resistance. So E. Number 19, potential difference. This is just talking about voltage. The potential difference from X to Y when the switch is closed compared to when it's open. So either way, the potential difference from X to Y is the voltage of the battery, right? Whether you keep adding in 1,000 resistors in parallel, this is going to be the voltage of the battery. unless you put like a resistor here or here, like within the path to get to from the battery to X to Y, then you're not changing that voltage. So it should be equal either way. So here I'll say the voltage across XY is the voltage of the battery, adding more branches in parallel will not affect the voltage across X to Y. That's a weird way of saying it, but from X to Y, or across that branch. Alright, what happens to the current through the battery when the switch closed? Current through the battery is I total. I total is V total over R total. Total voltage is still the same battery, so that's the same. Now you are changing the equivalent resistance. You are adding in a second resistor, but you're actually decreasing it. So you should have, because this is in parallel, the more you put in parallel, you actually decrease the overall resistance. So this decreases, which means that this should increase. So here, the total current is going to increase because you have the same V total, same battery, but you have less equivalent resistance because you added the resistors in parallel. So the same voltage with less total resistance should increase the total current. Right here, still talking about voltage across XY. Right now, the voltage across XY is just the voltage of the bulb. Oh wait, we're not there yet. Just talk about the current right now. Alright, so when the switch is closed, what happens to the current through A? So think about before, it goes through A, B goes around. When I close the switch, it's going to go through A, around, and like this. So I will take out a resistor. These are in series. If I take out the resistor, I have less resistance. So I equals V over R, same total voltage, but less equivalent resistance is more total current. A is getting that total current, so it will increase. Alright, here, so we would say increases because A gets I total. You have the same V total with less R total, so you get more I total. Alright, potential difference across A. So I'm going to rearrange my equation to V equals IR. Now I'm talking about just A in particular. The resistance of A, it's still the exact same bulb, so this should be the same. The current, we just said that the current through A increased, so then we should be getting a greater potential difference across A. So this should increase because you have bulb A has the same resistance with more current. Now, greater voltage across A. The other way to say this, actually there's another easy way. So I went the current route because we had just explained it, but you could also say before A and B were splitting the voltages, whereas now because the switch closes, it's going to skip bulb B, so now A gets the total voltage of the battery. That's another way to explain it. Especially if you hadn't already done this, right? Just think the voltage way. You'd say, oh, well, they're splitting it right now, but if I skip it, now A gets all the voltage of the battery. What happens to the potential difference from X to Y? So before, I'm going to make a note, before the voltage across X and Y was just the voltage across the bulb B, which is like half the voltage of the battery. Now, the voltage across XY is literally the voltage across this wire right here, which would be 0 because it's just a wire. There's no like energy being used up, no potential energy change. Remember, voltage is the difference in potential energy from one point to another. From one point on the wire to this another point on that same wire with nothing in between, you wouldn't have any change in potential energy. So we should say that the voltage across XY decreases, particularly decreases to 0, since the wire and the switch has negligible means, sorry, I had to spell it out. Negligible means so small that you can ignore it, so it has negligible resistance. We're going to pretend we live in a super ideal world where wires basically have no resistance. So since the wire has like no resistance, it has negligible voltage across XY. So, doesn't look like a word. Here, right, because remember voltage is I times R, so yes, I definitely still have current going through it, but if I don't have any resistance, right, none of that energy is actually getting, like, changed. And then I would make a note before the voltage across XY was the voltage across bulb B. Now it is skipped. So, that was why it decreases, because yes, I explained why I went to 0, but I'm explaining that there was some before, because it could have been 0 and 0, but it had some and now it's 0. Alright, here we've got 3 resistors, they're all identical. When the switch is closed, what happens to potential difference across 1? Justify. So similar to what we were doing, I think on, yeah, kind of, not really actually. So here, when I close this, now I have in parallel, so I actually just decreased our total, because I added some in parallel, which is going to increase the total resistance, total current. Now R1 gets the total current, so R1 is getting more current than before with the same resistance, so they should get more voltage. So let's go ahead and explain. So the equivalent resistance of the circuit has decreased. Decreased because you added resistor in parallel. So that increases the total current that R1 has, because R1 is getting the total current. So now I have more current going through here. So V equals IR. We're looking particularly the voltage across 1. This has increased, the resistance stays the same, so now R1 is getting a greater potential difference. So R1 has the same resistance with more current. It has a greater potential distance across R1. What happens to the potential difference across R2? So 2 ways to do this. I kind of explained the current way up here, so I'll do the voltage way. So the voltage across 1 plus the voltage across 2 still need to add to the voltage of the battery. So because, even though I added another loop, that just means that V1 plus V3 also need to add. Because we just increased the voltage of 1, that means this one must decrease, they still need to add to the same total. So since V1 increased, V2 must have decreased to still add to the same voltage of the battery. Alright, here we are talking about power. What would all the other powers be? So the first circuit is P. So I'm going to call these general variables. This one has a voltage V, has resistance R, it'll have a current I. This one has an R total of 3R. which means when I plug in I total, still the same V total, right, V, but now it's over 3R, so then this one would get 1/3 the current, 1/3 the current. Here, this one, same idea, but it's only twice as much resistance, so I'll get half the current. And here I'm going to do total, so 1/2R plus 1/R equal, and 1 over that, so that would be 1/3R, which that's not right. Just kidding. 1/2 plus 1 is 3/2, so 1/3 R, so this is 2/3 R. Which then would give me 3/2 I. Is that right? Okay. The other way to do that is, actually there's a simpler way. Instead of trying to find R total in terms of R's, here, right, these would both get voltage V. So then this guy would get the current I, this one would get only 1/2 I, which means that your total current would be 1.5 I, which is 3/2 I. That's an easier way of doing it. So here I found the total currents for all of them. I'm talking about the power of the battery, so that's talking about P total. So here P total was just I times V. Here I'm going to do I times V, but it's 1/3 I times V, so see how you get 1/3 the power. Here I have 1/2 times V, so that is going to get half the power. Here I have a total current, right, because we're talking about total power, so I did total current times total voltage, that would be 3/2 or 1.5 P. Okay, that was it. I've actually calculated all of the powers. So A is P, B would be 1/3 P, C would be 1/2 P, A, B, C, D, D would be 3/2 P, or 1.5 P. Alright, if each circuit is connected to a battery with the starting voltage of V, if each circuit was connected to the battery at the same time, rank each circuit for the length of time that the bulbs would be lit. So long time means it's not using energy at a fast rate. Short time, right, if they don't last very long, that means it's using electrical energy at a fast rate. Because if you use it up really fast, right, it doesn't last very long. So the length of time from longest time. The longest time is the not fast rate, so that is the least power to most power. So the least power is the 1/3, so that would be circuit B. And then 1/2 is next, C, and then 1, A, and then the highest power was D. I just labeled these A, B, C, D just to make it easy, by the way. But we should actually label them if we're going to use that in your answers. So just, if you were to do that in free response, right, like actually label. Alright, and then our explanation could be the longest time has the least power because uses the least amount of energy per second. So if they all start with the same energy, right, because they're all starting with the same voltage, A will take longer to run out. Alright, here potential difference from X to Y when the switch is closed compared to when it's open. Oh man, I shouldn't have written over it. Okay, so when it is open, so when it is closed, let me start with that because it's the easy one. If it's closed, then it's just a regular parallel where it skips over this guy. So if it is closed, then the voltage across X, Y is the voltage of the battery. If it is open, then it's only part of the battery. So open, it's only, right, delta, the voltage across WZ plus the voltage across XY have to add up to the voltage of the battery, so then it would have to be less. So the potential difference when it is closed is more than when it is open because it's the battery compared to when it is part of the battery. So if it is closed, the potential difference across XY is the voltage of the battery because the switch Wx will short or skip over the, let's call this R1, R2, and R3. We'll short R1. When it is open, the voltage across R1 and R2 must, I would say, actually, R1 and R2 must share the voltage of the battery. So the voltage across 2 is less when open. Whew, okay, potential difference of YZ when closed to when open. So when it is closed, then that's just the potential difference of a wire, which is 0. And when it is open, that's just potential difference across V1, which is a number, right? So when it is closed, that is less, so very similar to the one we did over there. When it is closed, the potential difference across WZ is 0 because there's no or negligible resistance in the switch / wire right there. Wire. When it's open, the voltage across WZ is the voltage across R1, which is not 0, so 0 must be less. Okay. Remember, multiple choice is on Monday, for responses on Tuesday.